In this video, we're going to learn how to calculate the speed at which a wave travels through a string. So we're going to start with a piece of string, and we're just going to apply a tension in the x direction. We're then going to continue to apply that tension while lifting the string up, sending a pulse through the string. So more and more of the string is going to be at motion based upon the speed of the wave v, which is what we're trying to calculate here. And we have lifted the string up at a rate of velocity in the y direction, so how much the string is raised up is going to be vy times t, because we're using the idea that velocity equals distance divided by time. And then v times t is the distance that the wave has traveled forward. So we now have an x and a y component to the tension in our string, which is going to give us a force that's actually a little bit greater than this fx that we had originally, so the string actually does stretch out when we do this. Alright, so the first thing we're going to do is apply the impulse momentum theorem, the idea that the force times time is equal to the change of momentum, or mass times velocity. Initial is going to be 0 here because initially the string was at rest. So we're going to have Fy times t equals the mass of the string times Vy. And then we're going to use the law of similar triangles, so we're going to do Vy over Vyt, Vx, and then Vt, because we're putting our y motion together and our x motion together. I'm just using the law of similar triangles. Now I've just rearranged the second equation we've made to solve for a force in the y times time. So notice we have force of y times time, force of y times time. So we can equate these two to say that the mass times velocity in the y is equal to force in the x, velocity in the y times time, divided by the speed that the wave is traveling forward. And you're going to see that we're going to be able to cancel out Vy on both sides. But now we're going to do something with the mass. The mass of the string that's actually in motion is going to equal something called the linear mass density, which is the ratio of the mass to the length of the string, times the length of the string that's actually in motion, which is the velocity times time here. So the speed of the wave times the time it's been in motion. So multiplying those together gets you the mass of the string that's actually in motion. So the rate of mass per length times the length that's actually in motion. So I'm going to sub that in down here for mass. So I've already said we can cancel out the Vy's on both sides, and then we can cancel out the time on both sides. So rearranging, we get that the speed of the wave is equal to the square root of the tension in the string divided by the linear mass density, where the linear mass density is mass per length of string. And this is something that should conceptually make sense to you, because when you go to tune a string instrument, you change the tension in the string. So that's why there's usually those little knobs at the end of a guitar or a bass or a cello or whatever, where you actually change the tension in the string in order to actually tune the instrument. So change the speed of the wave travels at, and therefore the frequency of the note that you're getting. You also understand that mass per length matters when it comes to the speed of the wave, and thus eventually the frequency. Because if you look at these strings on a guitar, they're not the same width, so they're all going to have a different mass to them, which is going to change what speed the wave travels through them. And you also see between different types of string instruments, between guitars and basses and cellos and violins, the strings are very different in mass and length to each other, and that's also going to have an effect on the frequency that you get whenever you play those particular strings. So we already conceptually understand what is coming out of this equation, because we know we use tension in order to tune an instrument, and mass per length matters when it comes to the types of notes we expect from that particular instrument, because that's why we have violins versus guitars versus cellos versus basses, etc. The next video in the list of videos is actually someone stuck an iPhone inside of a guitar, so you could actually see that the width of the strings are different, and you can actually see how that affects the waves that travel through those particular strings.